We'll have a quiz on Friday. Okay, just whatever have been covered in the lectures and in the quizzes and in the labs. Okay. Most likely it's going to be something similar to the homework assignment you are going to turn in on Friday. Okay, so you are prepared for that. For lay out a transistor that you have done this in lecture VSI. Do you recognize what are these materials or what are the layers in here? What is this? Polysilicon. So that's a gate, right? So this is a diffusion, right? So you have two contacts. That's a via, but that's metal 1. And the length of the channel is this or this? Which one is the length of the channel? The second one. So this is the length, right? I should know that only the channel under the gate is effective channel, because all the other areas are not having any electric field, so it's not actually a channel. So the channels or the width of the polysilicon here defines the length of the channel. Keep in mind. So that's the length of the channel. Okay. So what if we want to draw a pretty long channel transistor? NMOS, for example. You do have wire poly, but it's just taking a lot of space. I have to probably do this, right? I have two contacts here. And like that as a poly. You can definitely do that, but usually we don't do it that way. Okay. In parallel will be in parallel, not in series, right? Oh yeah, put them in series, yes, like this, right? Yeah, because the way how you connect them determines you are putting them in parallel series. So eventually I'll have two terminals. One is input, one is output, right? So you can make a longer channel. But what if it's super long? Super long, then you have to extend it in one direction, but you do have a limit eventually. You know, it's going to be super long. So there's another way to do that. You know, for example, if you have, you just make a diffusion here, just this, the same footprint, for example, and then you draw your gate in this way. That looks odd, but you can make a pretty long channel and which covers a smaller footprint instead of just extend it in one direction. So this is still the N plus. Okay. Let me see if this is right. Actually not. So this is the active or the diffusion or N plus in the case of CMOS. And the entire thing here is poly or gate. So will this be a long channel transistor? So you can have a terminal here, like a via connect to metal 1. So the channel is N plus, right? It's a no, channel is not N plus. Channel is active. It's not even diffusion, sorry. So channel is just the active. It's the opening on Fox. Okay. So you just design the channel to be that long, and then you put a gate on the top and you apply electric field on the top. Then it's gonna attract electrons into the channel to get a long channel like that, instead of just draw one direction, just extend it in one direction. It's one example. As the reason I want to introduce the long channel because we use the wider channel, not longer channel, but wider channel instead of the longer channel a lot. So what if you have parallel transistors like this? The reason they are in parallel is because I shorted all the source and the drains together. Again, they share the same gate. Are they in parallel? Yes. So channels are in parallel, definitely. So this, for example, each one is W over L, width over length. And the whole thing here is equivalent to one wider transistor. So what is the width and length of this wider transistor? So actually in your layout, if you have 4 transistors laid out in this way, and it's going to generate the same amount of current if you draw a wider one. So if each one is W over L, then what's the equivalent one here, the width and length ratio? Yeah, for W over L. Does that make sense? So it's getting wider. And remember the IDS square law equation is KPN over 2 and W over L and VGS minus VTHN square. This is a constant, and this is something applied by the user. It's not controlling anything. If you have 5 volts in digital circuits, it's always 5 volts for VGS. So this is the only parameter controlling the current. And you are using the minimum length usually, or in the lambda rules, you use 2 lambda as the length. So the only parameter that controls the current, amount of current, or the capability of driving the capacitive loads, it's going to be the W here. If you make it wider, right, in the inverter you did in the lab last week, yesterday, if you got a wider transistor, you are able to drive a bigger capacitive load. Okay? So W will be the critical parameter here you can control. So how to lay out this kind of transistor? It's very interesting. If you have a in any of the VLSI tools, EDA tools, for example, electric VLSI or Cadence, if you lay out 4 transistors in parallel like that, and you can replace it with one wider transistor, that's going to still pass LVS or NCC in electric VLSI. Is that interesting? It's going to work. Okay, so it's considering this is equivalent to 4 smaller ones in parallel. Okay, so how to lay it out? So you can lay out a wider one. So the wider one should look different than this one, right? So wider one will be this or this. Which one? Wait, a wider one should be this. There's a gate, right? These are the VS, or this. The second one is the wider one? No, this is the longer one. That's the channel. This is the drain is the source. So this is the channel. You may need a bigger poly. Okay, That's the length of the channel. That's the distance the electrons are going to travel. So that's the length, okay? And this is the width. Why? Because you can imagine you got all the electrons getting ready here. You're definitely getting a wider channel or wire for the electrons to go through, right? The length is still the same compared to compare this one with this one. Same length but wider channel. Okay. So how do we lay out these 4 transistors? You can do one by one, right? It's the simplest way to do it. Like this. 1, 2, 3, 4. How would you like to draw the gate? So they're in parallel, okay? Do you want to draw the gate vertically or horizontally? And why it's different? Vertically? Would that be an easier way to lay that out? Or you just draw a gate, 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 gate. Then just directly connect the poly. And here's your drain, right? Here's the source. No, you are not doing opposite. You are doing the right, the correct way, because the transistor schematic, you have gate, drain, source, right? So for layout, gate, drain, source. Because they are not, you don't have many of them being put together parallel, right? Oh, another reason for that is for the inverter, right? You're talking about the inverter we did, right? Yeah. Yeah. Because we have a CMOS, not NMOS, and you have PMOS on the top and NMOS at the bottom. So you have the poly being put together like that, so you can directly do this connection for the gates. Yeah. 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 You just like that, right? Yeah. For which one? For the ones we did? Mm-hmm. Yeah, but whatever way will make a shorter poly for you to reduce introduce less resistance in the circuit. So always do it that way, because you can have the 2 gates of polysilicon sticks being aligned to each other, so you can directly draw a line here to make them connected to each other. And also for the metal, it's fairly easy as well. You have a what's that called? Remember, the top and bottom. So they are shorted to VDD and ground, right? But what are they called? Why do you need a thing? Why just not draw metal and put a VDD for the metal? But you put something else. It looks like there's some diffusion N plus or P plus in there. Yeah, it's called. So this is PMOS, right? On the top is PMOS, and the bottom is NMOS. Okay, and you need a watt on the top, and you need a watt at the bottom. The cross-sectional view of it. So for N plus, do we need a well? No. For P plus, do we need a well? Yes, because P plus is shorted to the P type, the P sub. So what you need N plus. So this is N well. You need to place P plus in N well. So it's not shorted together. And how do you make the connection between P sub and ground? You dope a P plus in here. So P, the same materials are shorted together, okay? And then you ground it.
Why do you need to do that again? Dope the P plus?
Yeah, because you want to avoid any parasitic diode. So you just short all the P's because this is the pin junction, right? And you don't want to forward bias the diode. So always short this one to ground or the lowest.
I get why you short the P substrate to ground, but why do you need to do P plus again?
Because P plus and P, they are the same materials, they are shorted. So you don't want to directly put something here at the bottom. There's no way to do that. You have to flip the wafer and put a metal. There's no way to do that. So you have to have something like intermediate material in the middle, so you can connect. This is metal, right?
So P plus allows
yeah. Oh, you are talking about why not directly using a metal to the P, because the P plus is heavily doped, just more concentrated, just more conductive. And there's another name for these two nodes actually. Yes. It's called a well contact. And now the name makes more sense. It makes a contact to the well. But here you don't have a well, but the P sub is considered as a well. The whole substrate is a well. It's a P well. Okay, it's a well contact. Or another name I forgot if that's accurate. I think it's like well tap or something. Also makes sense, right? It's a well tap or they have all different names. Okay, yeah. So for this one, it's called P type, and for this is N type. So when you are using Cadence, and you can find out the components in the library have different names. A lot of times it takes you a very long time to find out the correct one. If you have a lot of experience with different technologies, you are searching like N well, P well contact. If you couldn't see it, you'll start searching for like N type, P type. You have like hundreds of components in the library. If you are manually pulling them out from the library into your design, you have to search for that. You have to type the name in there and press enter. You get frustrated. Like you put a P contact, enter, nothing. Okay, so you can start blaming this technology. They didn't even put a like well contact in there, but actually they have a different name.
In digital PS or electric PSI, what is that end of represented by? Is it like built in when you put the transistor?
There's a specific layer. I think it's either slash or slash dot. I forgot, but it's a different color or pattern.
Because you said like the background of the layout screen is all P type, right?
Yeah.
And you're putting things on.
That's right. For most of them, but some of them are not. I forgot which one. I think that's when they are using P, they probably have to specify that. Otherwise, it's just no background at all. It's confusing. Let's don't get into the too deep into the colors. Yeah. That's right. So in some of the layouts in the future, you may have to consider that. But now, because everything, all the PMOSes are being put in the same well, and all the NMOSes are being put in the same well as well. So we don't place the transistor at different wells. We don't do that. But sometimes in the design of the charge pump, we are going to use it for one of the circuits, but we're not going to design it. So we need to place that transistor in a different well. So in that case, the way to lay it out is going to be different. But in here, it'd be very helpful to explain this now, so they're not getting confused. I have a few questions if you look at the layouts here. Let's see these ones. So we got more transistors in here. Okay. Let's move to the. I got that figure here. Fix it. Okay, like this one. So the dots must be the N-well. The slashes must be the P-well or the P-sub. Okay. And you see that there's an overlap, right? At least you have to move. So grab this part and then you make it longer. It's easy, right click and change the property of it, right? So you got a longer N-type or P-type. Just make it easier. Let's just use tab. Easier name. So on the top, is that an N-type or P-type?
What?
I'm not saying TYP, I'm saying TAP. Yeah. Is that an N-tap or P-tap? So think about tap, it's just a, make a contact or touch. You know what I mean? And is this one an N-type or P-type? So the squares are vias, right? No issues on that. The N-type, why the N-type? PMOS is in the, are in where? In N-well. So it is the N-type because it is tapped well. So the N-well is the body of the PMOS. So you need to place this. Okay. So that N-type must be a N-type material, right? N+ material, in order to make the contact with N-well, which is the body of the PMOS. So basically, you cut. It's being drawn in a different way, but when you are looking at this guy, you should know that this is a top view, right? You are fabricating PMOSes on the wafer. So you got PMOS here, channel, okay? PMOS and channel. Do it on the camera. Okay. For example, that's the PMOS, two vias. And here's the channel, right? And your N-type is on the top. If this is on the silicon wafer, N-type is on the top. And they are being built in the same well. And that's a 3D structure, that's a 3D component. Okay, it's going to be different from this one. This one is a cross-sectional view. But if we are, for example, I'm asking you to draw a layout view of this part, what that looks like from the top. It's going to be a transistor. What else? Where's that tap? Tap. Yeah. Right? Make sense? Okay. Same to the NMOS. Got P-tap, short to the P-sub. That's why you placed this thing here. This thing will dope P+ in it and provide a via so you can connect to metal 1. Okay? And this component is a part available in the library, and this part already has metal 1 on it. So you can see when you introduce the metal 1, make the connection to it, it doesn't draw another metal one layer on the top because it already has a metal one. Couldn't see it, but I think that's why the color here looks like more light green and this is more dark green because it already has a metal one on it. So when you are introducing a wire of metal one and connect the two here, so the whole thing has a metal one already. So directly make the connection easily. And another thing is, you see the transistors slashes represents for the NMOSes, right? So slashes represents what? So that's a different case. The P-type substrate, okay? But see, this is a P what? P-type, P-T-A-P, right? It's a P-well contact or P-type, okay? So I added another P-well here. Did you see that? See, it's in a different dimension because it's sometimes difficult to draw the same dimension, but I can tell. So this is added. So this part is added to it. You know what I mean? As a pure well layer. It's available on in the library as well. Why do I have to draw that thing? The same to this the unwell. See, I couldn't see that clearly, but I did that. So you grab a PMOS, it comes with that unwell because by default it puts unwell, put the PMOS in the unwell. But however, if I don't draw another unwell rectangular shape here, there will be a gap in between the PMOS unwell and the N-taps unwell. You know what I mean? I drew a rectangle here to connect them. It's a pure well layer. So if I don't do that, what's going to happen? In a cross-sectional view, what's going to happen? If I don't draw that pure rectangle shape in the middle to bridge them, do you know what I'm saying? So I got an N-type on the top, right? Has all the dots. So the dots came with that part. I grabbed it from the library and it has a ring of dots. And the PMOS, I grab a PMOS, a few PMOSes, and has a ring of dots because the PMOS are supposed to be built in the unwell by default. But there's a gap. So if you look at it from the cross-sectional view, what's going to happen? What's happening here is I got P plus, For sure, these are in the unwell because that's by design. Yeah, their unwells are separated. That's the N-tap. It's also in the unwell by design. So there's a gap. So you are shorting this to VDD. You are thinking that you connect the connect N, you know, of the pin junction to the highest potential, so it's not getting forward biased. Okay, is that happening? No, because the unwells are two separate wells. Okay, so I placed a dot, pure dot layer in here, so the fabrication, the foundry knows it's one piece of unwell, right? It's a one piece of unwell.
So if you are laying out that same process, but you type in the background, technically you wouldn't have to connect them because the background is also typed by default.
Mm-hmm.
But
yeah, that's right. It's confusing the foundry. Like, you need a different wafer?
Yeah. Okay, that makes sense.
Yeah. Okay. So if you have a big design, like the ones let's look at some of the examples here. And also it makes a lot of sense why you want to lay out your transistors that way. Okay. Put them in one line for a group of transistors. So what if some of the complicated designs, not really, but a little bit larger scale, how to do that? So this is an 8-bit mux, and let's take a look at it. So what the mux looks like. Yeah, this is easy, right? This part is easy. Is there a problem here? Did I draw a pure unwell layer to cover all of them? I didn't. Is that a problem electrically? I know it's not a good practice, it's not ideal. But is there any issues? Is there a problem with it? Like functionality wise. Think about the cross-sectional view, right? How the wells are being connected. Are the unwells being connected? Even though they are not in the same unwell, but they are actually. Yeah, by the metal. So unwells are still shorted to the same potential actually. Yeah. So not ideal, but it's gonna work, right? But still, for good practice, you should cover everything with in the same well. Okay, physically. Because that's the same voltage node, that's the same VDD. So you should connect them to the same VDD. They are shorted together, right? So if they're not shorted to the same voltage, for example, you have two VDD, two different power supplies in the circuit on the wafer, then there should be many different cases, but they can be in different wells because they have the same different potential, right? So what about these ones? So the have different groups of transistors, right? This happens a lot, not just in this kind of slightly larger scale circuit, but in the VLSI circuit, there are just maybe many of these blocks in there. How do you still need to do that? I mean, put all the PMOS in the same well. It's impossible, right? How to do that? If you zoom in, like you see, this is the top rail at the bottom rail. For the groups of transistors, they are for one functionality or one gate, or not one gate, probably one component in the circuit. You definitely put them in the same well. But you have another group of transistors over here are super long distance from here, so you don't have to do that always. Just keep the same ones are just for the functionality of that component in the same well. It's impossible to keep, for example, the PMOS is here and the PMOS is here in the same well. How to do that? But you connect them through the metal instead of the piece of pure wells. Okay. And there's a way that you can lay out 4 transistors in parallel. It's pretty interesting. And we use, for example, this mark to represent the PMOS. And this is for NMOS. So this is the gate. And that's that's 2P plus. And that's 2N plus. That's a channel to simplify the drawing process. So for a inverter, we draw it this way. Show the gate, input, output. So this is called stick diagram. It helps simplifying your layout and or optimizing your layout manually, but definitely not using all these auto routing tools. Simplify something, okay? So for 4 transistors in parallel like this, how to draw it in the stick diagram like this. So got 1, oh, it's NMOS. NMOS is going to be circles, right? 1, 2, 3, 4. I want to bring Ian's question back here. So why we don't draw it this way? when we simplify the layout by using stick diagram, why we don't draw it this way. So here's the schematic, okay? Schematic. Why we draw it this way when we want to simplify it? Because that's the way how we laid it out over here in the circuit, right? So we have the gate runs like this. Okay, we got a circle, circle, gate. Circle, circle, gate. So simplifying here, it can directly translate it into the layout, physical layout. We manually laid it out, okay? Now let's see, how do we put them in parallel? It's very interesting to look at. They are thinking if I short them like this, and they will be in series. Not really. It depends on how you make the connections on the top. So before we do that, let's simplify this first. So for example, we can do this, and you can see the diffusion here becomes redundant. You got two and the metal connecting them together. You can overlap them, become one N plus. So it becomes this. Merge two into one. Okay. And still the channel. One. You merge these two into one. So got a gate here. You merge these two into one. Got a gate here. You merge these two into one. You got a gate here. So they're equivalent. So you can draw these four transistors in parallel really quickly, not in parallel yet, but we can draw four transistors in a line very quickly by doing, since if you know you have four transistors, you just directly draw 5 circles. 1, 2, 3, 4, 5. And draw a line, 1, 2, 3, 4 transistors. So how many gates you have, how many transistors you have. The gate is the input signal. So you have a gate, you got a transistor here. You got a gate, you got a transistor here. You got a gate, you got a transistor. Same thing with this one. How to make them in parallel?
You would alternate which one of the dots.
Yes.
And which one's the output.
Mm-hmm.
Like high output, high.
So what if I have a connection like this, metal, okay, this is the metal on the top. And I then connect these two at the bottom. Introduce 2 wires. Let's take a look at this, okay? So for a parallel circuit, it's just making different branches from one node, right? That's in parallel, just dividing the current. So this is one metal node. Keep in mind, this is important. It's going to be like another week or 2 weeks. Just you guys are going to work on stick diagrams to simplify our layout a lot. So I have to understand this first, okay? So this is the first example you are going to work with. So 4 transistors in parallel, and this is going to be the same circuit as this one. It's going to pass LVS. Why? Because here's, for example, current flows in here. And 1, 2, 3. Okay? Current flowing here into the drain, into one drain of the transistor, like this, right? Flow into one drain of the transistor, flow through the channel. Okay? We got another one, flows through the channel. You got 2 branches. So 2 transistors in parallel already. Same thing to the other side. One more transistor and one more transistor. So it flows across the gate, which means it flows through the channel as one of the branches. And these four are in the same hierarchy, the same level, same layer, same branch. So basically you have one current being split in four equivalent currents. Same thing, 1, 2, 3, 4. Okay, so now let's look at the output. Are they merging at the same electric node? Do they merge in the same node? Yeah, why? Why they merge to the same node? So these two branches, see these two branches merge here, right? These two branches merge here, and that's the same wire. Even though I drew the four transistors in the line, actually they are in parallel. Is that magical? Seems like they're in series, but depends on how you draw the wires, how you make the connections. So you can still make them in parallel. And if you draw this in layout, if you draw this in your schematic, you'll be able to pass LVS or NCC. They're the same circuit, so the EDA tools understand it, so don't have to worry about that. Make sense? So in your layout, how can you structure that with the real physical transistors? These are the gates. So there's NMOSes. So you can draw the green diffusion, connect them together, and find out you get two diffusions. They are basically doing nothing. It's just redundant. So you can merge them into one, right? So eventually it becomes this. So two becomes one. But still have two channels, right? Same here, you can merge these two into one. So just share. Same here, two into one. One, two, three, four, four gates. So four gates, four transistors. How do you connect them in parallel? The same thing like this, right? So got a metal one layer, a metal one, it's a metal one trace, a metal one, and here's a VDD. Just metal one connect to the, oh no, this is PMOS, right? This is NMOS, so you have a ground, so you have a ground bottom rail instead of the top rail. So this connect to whatever the signal on the top. So this is your, so for NMOS at the bottom, the N type or P type for the well contact, P type. And it's grounded, right? What's next? Get a metal one, connect to the p-tab. And you are thinking, I want to do it different in a different way. And do this first. And then would that be different? Let's connect to the type, right? Is that different? Is that going to make the circuit different? But which one's better? Do you have any opinion on it? Why would you think? I couldn't actually tell in this case, but sometimes you can tell. If you switch it, sometimes you cannot get the wires out easily. So that's how you use the stick diagrams to optimize it. So you use different colors and markers when you draw it. You can find out, hey, if I draw it that way, then I cannot introduce a wire to the polysilicon easily because I'll have 3 layers of metal. Right, but this one, I didn't see any really significant differences in here. Any questions on this? So we talked about the VDS and IDS, and this is saturation, and this is linear. What's the name of this voltage? VDS set equals what? If I connect the NMOS transistor this way, what's going to happen? D, G, S, what's going to happen? What? VGS equals what? Yes. Yeah. So we can substitute VGS with VDS, right? So now VDS set equals VDS minus VTHN. So what's the conclusion here? Why? Because the condition is VDS must be larger than VDS set in order to put this one in saturation, right? By looking at the curve. here's saturation, this direction saturation, so VDS must be larger than VDS set. And now VDS set equals VDS minus something, so it's always larger than so VDS will be always here, right? Always here. Okay, so it's always in saturation. What about PMOS? For PMOS, on top is S, keep in mind. If you want to make the similar connection, you are shorting this one here actually. So this is going to place the PMOS in saturation forever. Any questions on this? So there will be a little bit more something else regarding square law equations to calculate the switching point of the the inverter. I think we can do it on Friday. But you guys should be ready to do the homework. The homework 3, I think, which is due Friday. Yes, since we did the C5 layers. Any other questions before we wrap everything up here? No? All right, I'll see you guys on Friday.